covered in class, some of the examples in the notes. You know, if I ask you, what boils at a higher temperature, methane or neon? You would say, well, methane probably does, right? Because neon's a noble gas, it's small, all of that stuff. Yeah?
Could you touch on some gas versus condensed phase properties?
Sure.
It kind of fills in with this.
Yep, so where are the molecules closest, in gas phase or liquid phase?
Liquid.
Liquid, right? It's condensed, which means the molecules are close together. So in what phase are the van der Waals forces higher? Liquid or gas?
Liquid.
Liquid, right? Things are sticking together. And so that's the most important thing about the liquid phase and the gas phase, is that in condensed phases the molecules are much closer together. So here we might have liquid. Here we might have gas. Whoops. And so if they're just van der Waals or dispersion forces between the two, between these two molecules, how does the force between them scale with distance?
More distance equals weaker.
More distance is weaker, right? Do we know the mathematical relationship? Is it? So more distance is a weaker force, right? So if we take the force, or the energy between them, we know that as the distance increases, energy is going to go down. What's this exponent right here?
For what type of force?
6.
6 for what?
Dispersion.
6 for dispersion, right? What about Coulombic forces?
2.
2, right? So it's important to know at least some of these functional relationships, and I think a lot of these equations were on the sheet for your first exam, so I'm going to take the sheet from the first exam. It'll be on the back of the final, so make sure you at least know your way around some of those basic equations. And you all have your first exams. The equations that I put at the end of the exams are probably relevant to the problems in some way, so make sure you look at all the pages on the exam and have those sheets. Or not, you don't have to bring those sheets, I will provide them, but make sure you know what all those equations are, because those were probably important. So so this is condensed phase, and this is gas. So those are some of the important properties. Yeah?
How does polarizability relate to certain factors like boiling point, things like that?
Sure. So polarizability generally, larger molecules are more polarizable. So if you have something that's, we'll take easy examples. So say you have fluorine versus iodine, right? And this was a question on the first exam. So which molecule is more polarizable? Iodine, right? Because it's huge. It has many more electrons. Fluorine is pretty small. What else is special about fluorine? Very electronegative, which means it holds its electrons very tight to the atoms, whereas the electrons are, they're in larger shells for iodine, so they're out there more in this case. So which molecule is more polarizable?
Iodine.
Iodine, right? Polarizable means how can you shake those electrons around the molecule when you bring in something like, let's just make this a dipole. So if you bring this dipole close to iodine, you're going to push the electrons in iodine further away than you can in fluorine, because iodine has more electrons, it's holding on to them more loosely, and so iodine is much more polarizable. And so because of that, this will have a higher boiling point, because the molecules like to stick together, right? In fact, iodine at room temperature is a solid. If you've ever seen iodine crystals. Fluorine at room temperature is a gas, and so we know that neither of these molecules have permanent dipoles, right? And so iodine is more polarizable, it's got higher van der Waals forces. Higher van der Waals forces, more polarizable. And then that leads to the higher boiling point. And so polarizability really depends on how tightly the electron, how many electrons there are and how tightly they're held to the atoms. Which one would have the higher ionization energy? Ionization energy is what?
The fluoride.
Fluoride would have higher ionization energy. So ionization energy is the energy it takes to get rid of an electron all the way to vacuum. And so if the electrons are held more strongly with fluorine, this is going to have the higher ionization energy. This has lower ionization energy.
So you said there's higher van der Waals forces in iodine, but aren't they both dispersion?
Yeah, that's right. Yeah, so they're both dispersion forces. But the dispersion forces are just higher for iodine. So if you remember the chart where it has dispersion, dipole,
Okay.
hydrogen bonding forces, those can have different values, right? And so, yeah, so the forces can be the same type, but the dispersion forces are greater here. Yeah.
Could you touch on internal energy and a little bit how Born energy?
Was that on the exam? Or was that on the review sheet?
I thought it was.
So Born energy wasn't, but internal energy was, so let's talk about that. There's no questions on Born energy, that's, I'll just let you know that. I don't think there were any questions on Born energy on the second exam either, but internal energy is important. So we looked at charts like this, where if you go from, let's say, reactants to products, so you might have a diagram like this where you have both a delta E, so you have change in internal energy. And if you go from reactants to products, have you added or subtracted energy from the system? Added, right? You put energy in, and we often have some sort of activation barrier, right? And so we can also put delta G on this chart, delta H. Those are the three big ones. And so generally, when you increase the internal energy of a system, you're adding energy to it somehow. What are the two ways that we can add energy to a system? There's only two. Heat and work, right? So make sure you know your way around W and Q, because that was probably a pretty important lesson. And so we talked about exchange of Q, and we talked about exchange of W between our system and the surroundings. And then of course the universe equals system plus surroundings. There was lots of questions on this on the second exam. You guys did great on the second exam, and so hopefully you remember about heat exchange and work exchange, and that's the way that you change the internal energy of the system. So you did some calculations, some easy stuff on delta S. Delta S of the surroundings equals Q over T. We can figure out what the delta S0 of the system usually is, or we can figure out what the entropy of the system is from the tables and things like that. You should know the difference between a reversible process and an irreversible process. So what's the definition of a reversible process?
Universe is equal to 0.
Universe is equal to, the entropy of the universe is equal to 0, so delta S universe equals 0 for reversible process. And what's the main type of reversible process that we learned about? phase changes, right? So for this class, only phase changes. They were the only reversible process. Is a chemical reaction a phase change? No. Is combustion a phase change? No. Combustion's a chemical reaction, right? Is heating something a phase change?
Yeah.
Could be. I mean, you have to go through the melting point or the boiling point or something like that. What's the temperature change when you go through a phase change?
0.
0, right? So solid water and liquid water both exist at 0 degrees Celsius. That's the definition of a phase change. If you're just warming something up, if you're changing the temperature or cooling it, that's an irreversible process. And so the delta S, well, what's our other choice? If delta S doesn't equal 0, delta S of the universe is what? If it's not equal to 0?
Negatives.
It's positive.
Always has to be positive. Delta S of the universe is never negative. So delta S of the universe is greater than 0 for an irreversible process. So that's chemical reaction, heating, cooling, etc. So the most important part about internal energy, of course, is delta E equals Q plus W, which tells you that the only way to change the internal energy of a system is to move heat and work into or out of the system. That's it. So there was a question on the second exam. If you have a rigid insulated box and you don't let any heat and work move into or out of the system, the internal energy hasn't changed. You could combust stuff, you could do all sorts of stuff, but the internal energy doesn't change. So if you had a calorimeter, let's say you had one of these calorimeters where you have, we're going to put CH4 plus oxygen in here. Then surrounding this thing, and say we have 6 moles of methane and 100 moles of oxygen. Then we have water. Then we insulate this thing. So this is all insulated. So what does insulated mean?
Transfer of heat.